Morning, everyone. Everybody awake? Welcome to Pindemonium, a DBI-based generic unpacker for Windows Executable. This is the Jasmine Ballroom with Sebastian Mariani and Lorenzo Fontana. Before we begin, a few brief notes. Stop by the Business Hall located in Bayside AB. The Black Hat Arsenal is on the Palm Foyer on level 3, and of course the Arsenal reception at 5 o'clock. If you haven't picked up your merchandise today, is your last chance to visit the Black Hat Swag and Bookstore. And thank you in advance for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick up. Without further ado, here we go.
Okay, let's start. Hi everyone, I'm Lorenzo Fontana and he is my friend Sebastiano Mariani. Today we're going to talk about Pindemonium, a DBI-based generic unpacker for Windows Executable. Before starting, I would like to thank Fabio Gritti and Stefano D'Alessio who have contributed to this project with us. But now let's go straight to the point. When dealing with malware, two approaches are commonly used: the static analysis, which tries to study the malware without executing it, and the dynamic analysis, which tries to understand what the malware does by executing it and tracking its behavior. A reverse engineer is able to exploit static analysis techniques to understand the behavior of the malware by analyzing the disassembled code, the strings, and the imported function. However, nowadays malware tries to hinder the process of reverse engineering by unpacking and decrypting its real payload only during runtime. In this way, when dealing with packed malware, the analysis of the disassembled code and of the strings is impossible because the real payload is unpacked and deobfuscated only after its execution. And the analysis of the imported function is impossible as well, because they are obfuscated and they are resolved only during runtime. To deal with this problem, there are two approaches. The manual approach, which is very time-consuming, but it can adapt itself to deal with different packing techniques, and the automatic approach, which is much faster, can scale well with the number of samples, but it is difficult to make it work to deal with all the packing techniques. Our answer to this problem is Pindemonium. Pindemonium is a generic unpacker which tries to reconstruct the original malware from its packed version, but it also provides a set of functionalities in order to deal with a custom situation and specific problems. Pindemonium is based on Intel Pin, a well-known dynamic binary instrumentation framework. Before going into the details of Pindemonium, we need to have a brief overview of what a DBI is. A DBI is a tool which allows the analysis of a binary by the insertion of instrumentation code. We can see the program in the form of a control flow graph as a set of basic blocks. A subset of this basic block, which is terminated by an unconditional jump, is defined execution trace. The first thing that the DBI does is to identify the current execution trace and copy it in a heap allocated memory area called code cache. At this point, the DBI analyzes the code inside the code cache and allows the insertion of user-defined code with a granularity at the level of the instruction, basic block, or trace. Finally, the DBI starts the execution of the newly created trace from the first instruction inside the code cache. Moreover, the DBI provides additional functionalities like Windows system call hooking and API hooking. The key idea behind the Pindemonium is to exploit the capabilities provided by a DBI in order to identify the common pattern which every packer shares. In order to unpack their code at runtime, they need to write it somewhere and then execute it. However, this is just the first piece of the more complex puzzle of reconstructing the original malware from its packed version. To deal with this huge problem, we have divided it into 4 main steps. The first one, as I said before, is to detect the memory area which have been written and then executed. The second one is to dump this memory area and the process in a correct way. The first one deals with deobfuscating the import address table, which is a Windows data structure that is used to resolve the function belonging to dynamically linked libraries. And the last one, it tries to identify which is the correct dump among the many that have been taken during the unpacking process. Let's now start our journey. The first step is to identify the memory region which have been written and then executed. And in this way, we say they have broken the written XOR execute rule, also called W-XOR-X. This rule implies that a memory area is either written or executed and is valid for usual program. While packers, in order to unpack their code at runtime, needs to have a lot of memory areas which break this rule. We exploit the pin functionalities in order to identify this memory area by tracking the write instruction and collect their target addresses. Then we group together the these target addresses in a write interval of contiguously written memory areas. Finally, we check if every instruction is executed inside one of these write interval. And if this is the case, we say that this write interval has broken the W-XOR-X rule. Now let's see how this works through an interactive example. Here we can see the yellow boxes which represent write instruction, and the target addresses of this instruction are highlighted in red, while the blue box represents a generic instruction. On the top of each box there is the address where the instruction will be executed. Let's start. The first instruction performs a write, and since there are no write interval, a first write interval is created. The second instruction performs a write to an address which is contiguous to the previous one, and in this way we extend the already existing write interval number 1. The third instruction performs a write to a completely different set of addresses, and in this way the write interval number 2 is created. Finally, we have this generic instruction, which is executed, as we can see from its address, inside the write interval number 1. In this way, we have detected that the write interval number 1 has broken the W-XOR-X rule, and we can go on with the next step of our analysis. Okay, we have solved our core problem. Let's move to the next one, which is dumping this memory area in a correct way, and the process, the memory area and the process in a correct way. Once we have identified the memory area which has broken the W-XOR-X rule, we get the address of the main module of the executable and we dump it to disk. Finally, we invoke an external problem which is called Shilla that reconstructs the portable executable and set the address of entry point to the address of the instruction which has broken the W-XOR-X rule. This seems pretty simple, but have we already finished? Nope, because what happens if the malware unpacks its code on the heap? By following the previous step, we wouldn't dump the write interval that has broken the W-XOR-X rule and which likely contains the unpacked malware, but we will just get the main module. And when we try to set the address of entry point of the reconstructed PA, this wouldn't make any sense because it is pointing to a memory area which have not been dumped. To solve this issue, we keep track of all the heap allocated memory area, and when we detect that the W-XOR-X rule has been broken inside one of these areas, we dump it and we add it as a new section inside the portable executable. In this way, when we reconstruct it and we set the address of entry point, this is a legit one, and it is pointing to the new section that we have just added. However, we noticed that when we try to analyze this result, IDA was not able to resolve some references because they are pointing to memory area which have not been done. To solve these further issues, when we detect that the W-XOR-X is broken, we retrieve all the heap allocated memory area and we dump them. In order to avoid to dump the same memory area twice, we check the MD5 of its content and we dump it only if we detect that this is a new one or a modified one. Finally, we create a new segment and we have them inside the IDB file created by IDA. In this way, as we can see now, IDA is able to resolve these references and it is able to provide to the reverse engineer a more complete view of what the malware is doing.
Hi everyone. Now I'm going to introduce you some of other features of Pindemonium. As Lorenzo told you before, one of the main problems when you are dealing with unpacking is the obfuscation of the IAT in order to reconstruct a meaningful import directory. The first thing to do is to locate this structure in memory. In order to accomplish this task, we have used the same tool used during the dumping phase, Sheila. Once this structure has been found, we have to deobfuscate it, but since an algorithm that can deal in a generic way with all these kind of techniques does not exist, we have decided to put our effort into the development of a plugin system that can allow an analyst to write its own deobfuscator and integrate it inside our tool without modifying it. As we have seen until now, as a result, our system produces a lot of dump. So we need to find a way to identify the correct one in an automatic way. The basic idea we exploited is to give for each dump a quality index through a series of heuristics. These heuristics are usually employed by malware analysts during their analysis manually. The first heuristic is the entropy difference between the original malware and the current dump. And if these two values differ in a significant way, this could be an indication of the end of the unpacking phase. The second and the third one are based on the analysis of the current instruction pointer and the previous one. During our research, we noticed that a lot of packers, when they finish the unpacking routine, they make a jump of a significant way, or they jump into another section of the program. So if we spot one of these two behavior, these heuristics are triggered. The last one, and maybe the most interesting one, is the execution of a set of predefined set of Yara rules on the current dump. These heuristics can be very useful for two main reasons. For example, we can identify if the current dump matches the same rules of a known malware family. Or as another example, we can spot the presence of some kind of evasion technique inside the current dump that can be subsequently analyzed and defeated. Now, let's explain some of other advanced problems we have to deal with during our research. The first one is a very nasty one because it exploits the expansioning of PIN in order to break PIN itself. We have found this kind of attack in some sample packed with the Packer PSPIN, but we could better understand the whole attack directly through an example. PIN, as explained before by Lorenzo, never executes the original code inside the main module, but it rather collects a trace of execution and copies it inside the code cache on the heap. As we can see, there is an instruction that, if executed, can cause the crash of the entire program. So when the execution starts in the code cache, the first instruction overwrites the problematic one. But here we have to pay attention because the overwritten instruction is only the one inside the main module and not the one inside the code cache. So continuing the execution, the program will eventually crash, as said before. Since with a framework like PIN, we have full visibility of all the operation executed by the program, we decided to exploit this feature at our advantage. So before each instruction, we inserted an analysis routine that checks if the instruction pointer has been overwritten before, and if the instrumented operation is a write operation, we inserted another analysis routine that is responsible to get the target address of the write and insert this address into a list of written addresses. So rerunning the example before, we can see that the first analysis routine can correctly get the target of the write and insert this address into our list. Then the operation is executed as before and the problematic instruction is passed in the main module. But before the execution of the problematic operation, our analysis routine can correctly detect that the instruction pointer has been overwritten before. So instead of continuing the execution, we force pin to break the trace and collect a new one from the main module. And the trace, the resulting trace, is the one that will have been executed if without pin on the binary. The last problem we have to deal with was the process injection. And remembering the explanation about the WXORX tracker, we can easily understand that if a process writes its own code into another process memory, this write will be invisible to our tool. So we decided to exploit the pin hook functionality to hook all those functions useful to identify remote write and remote execution. And then the basic idea behind the algorithm remained the same, as the execution and the write will have happened in the same process. Finally, this is a screenshot of our report system produced at the end of the analysis. It can show the whole evolution of the programming memory during the whole phase of the analysis, along with all the values retrieved by the heuristics. Now, experiments part. We decided to test the effectiveness of our system against two families of experiments. In the first one, Pindemonium was tested against a custom sample packet packed with several different commercial packers, while in the second one, the test was conducted against a series of malware known to be packed and collected in the wild. In the first case, we were able to fully reconstruct a working version of the original program in 14 cases out of 17. And we totally lost only with the packer Obsidian, because PIN is detected as a debugger, because it employs some kind of evasion technique against DBI. Even in the second case, we were able to achieve some good result, because out of 1,066 collected sample, we were able to correctly reconstruct 63% of them. The major limitation of our tool, as anticipated before when we were talking about Obsidian, is that it does not handle any kind of evasion technique, neither the one targeting the virtual environment nor the one targeting the DBI. It also does not handle advanced type of packer, which, for example, encrypt and decrypt code on demand during the execution. And finally, the last issue, the last limitation, is the performance issue introduced by the overhead of PIN. So, to summarize everything in a few words, we built a generic unpacker exploiting the functionality of a DBI framework with the final goal in mind to reconstruct a working version of the original program. We can deal with several advanced techniques like dumping on the heap or process injection, and the result given by the test were quite good. Now I would like to show you a short demo. As we can see, our system has been launched with several flags on it. The most interesting are the first one, that the follow executable flag, that indicates that we want to follow and analyze all the forked process by the malware, and the plugin flag that tell us that we want to use a plugin during the obfuscation phase. As we can see from Process Explorer, a lot of processes are spawned during the execution, and all of them are correctly followed and analyzed by our system. There is also another flag, the third one, but we didn't explain it yet because due to time reason. If you are interested, you can read about it in the white paper on the Black Hat site. As a result, 3 folders are produced, and in one of them there is the working version of the original program. And as the last step, now we will see how the JSON file of the result produced by our tool will be parsed by our report system. We have to automatize this task, maybe. Here we go. There is the name of the program, its initial entropy, and the whole evolution of the program during the analysis. And for each dump, we provided also the result given by the heuristics. And if we analyze the current one, the dump number 6, we can see that all the heuristics are triggered correctly, and or even the list of the imported function is shown. If you are interested in the code, the whole source code is available at this repository. And that's it. Thank you very much. We have maybe a couple of minutes left for if you have any question. Thank you.
Please use the microphone.
You had cited performance as one of the constraints, the overhead of the performance, but I know that video was sped up, but what performance overhead are you talking about as a constraint?
It was speed up like about 20 times only for 30 seconds due to the time limitation of the tool, but
We need to do something like, I think, a 50 per overhead on the execution of the malware. But when dealing with the unpacking phase, usually is done at the first part of the malware execution. And so even if the overhead introduced is a bit huge, you can just you need just to wait for the unpacking, and since it is taking just the first part of it, you are able to see the unpacked version of the malware even if you don't run the complete malware
program. Yeah.
Okay.
I have two questions.
Okay.
This one works only on Windows, right?
Yeah.
Okay. The other one is when in your process, were you able to identify like a keys, the malware is encrypting and then try to grab the keys? Is it possible?
No, we just leave the malware to unpack itself, and we just dump the memory and try to reconstruct the original PA, but we don't.
Okay.
That's it.
Thank you.